Hello everybody, so I'm going to now try and explain my theory of quantum gravity all in 10 minutes or less. So just to begin with, what is a theory of quantum gravity? What do we really mean when we say a theory of quantum gravity as such? Well, let's start with the word quantum, because that's a word that usually gets a lot of people mixed up. A quantum is just the smallest indivisible unit of something that you can have in nature. And when we're talking about fields, such as gravitational fields, we're looking for something called a graviton usually. Which we consider to be this quantum of the gravitational field, in the same way that the photon, symbolized with this Greek letter gamma, is the quantum of the electromagnetic field, and in the same way that the electron, symbolized with this beta minus symbol, is the quantum of the electrical field. So yeah, when we're looking for a quantum of the gravitational field, it might be a little bit more complex than looking for a single particle. And that's sort of one of the underpinnings of my model, is that it might be a little bit more nuanced than that per se. So yeah, so you have two objects, A and B, and these might be anything. These might be atoms, these might be stars, planets, galaxies, anything really from the quantum level upwards that gravitate, right, that exert a force of gravitational attraction between two objects according to Newton's law. So there exists this force F between these two bodies. So what are these dots exactly? What are these particles that are bound around these objects most of the time, but sometimes, very occasionally, a particle will jump some meaningful distance away from the perimeter or the edge of the object and enter space and start exerting a force of attraction there. So what does it need to be? What does the particle need to be to exert a force of attraction? I would contend that it needs to be a charged particle. So what I think we're getting here are electrons from B quantum jumping or quantum tunneling to this other object A and exerting a force of attraction there over the protons in A, and vice versa. Likewise, the particles in object A are doing the exact same thing to object B. So what is actually going on here? You can say there's an electron from A here, just off in the background there, like so. That's a very big electron. And then there's an electron from B near the proton of A, or a proton in an atom of A. And that exchanges a W minus boson vector particle in exchange with W plus from the proton. I hope you can see that. So that's basically what's going on at a subatomic level there. And the sum of all those sorts of interactions, because loads and loads of these exchanges would be going on all the time, and you can figure out how many electrons per second you're likely to find in the gravitational field using this equation. So that's just the independent variable there, d over dt, and I'm setting dt equal to the Planck time, because I think that that's a decent assumption for various reasons that I do, just because that would be the average amount of time that a particle can spend in space without interacting with another particle, which I think is about the Planck time. We have the number of atoms, Na, over n dot average, which is the average atomic number, over this ratio, 4.17 times 10 to the 42, which is the ratio between the force of gravitational attraction and electrical repulsion. So then we get some number here for what I call the secondary electron density, and that's in electrons per second. So for the Earth, the amount of electrons you'd get per second would be something like 5.58 times 10 to the 53 electrons per second. So a huge number of electrons, basically per second, more than I could ever reasonably diagrammatize and write out here, you know. If I had, 10 lifetimes, I wouldn't be able to do it. It'd be such an enormous number of electrons. And we also know from Einstein's theory of general relativity that when we're looking for gravitating objects, we're looking for objects also that interact with light, that reflect light. So these gravitational fields are always reflecting particles of light, put a little gamma there just to indicate that it's a light particle. And sometimes a light particle or virtual particle of light will go all the way around an object and become gravitationally lensed around the object in the sort of zigzaggy pattern that you can see here, but which on very large scales, and considering the number of electrons that we have in the systems here, would look curved or would seem to be a curve. Right, so I think the electron, for all sorts of reasons, partly to do with things like supernova observations as well, observations of type 1a supernovae, we find that the neutrinos from those supernovae arrive on Earth 8 minutes before the particles of light do. And that's because if you can imagine that one of these dots, these A or B dots, are imploding stars, then we can sort of begin to see what's happening with the escaped light. All the light will just be falling back in on itself in the implosion of the star, right? And not going anywhere. Whereas the neutrinos, because they're not charged particles, and because they don't interact very often with electrons, whereas light particles do interact very often with electrons, those would just be escaping out into space. And therefore we would have, you know, this early detection of light particles. So, I mean, there's all sorts of additional subtleties to the model of quantum gravity that I put forward, but that's really the basics of it, I think. And, you know, it's just imagining everything surrounded by this very ephemeral, very mysterious cloud of electrons that, for instance, reflects light particles back into space. And we can see that, you know, the effects of that with galaxy clusters and so on, reflecting huge amounts of light back into space. Possibly since the Big Bang, 13.8 billion years ago, we've been getting this phenomenon of the accelerating expansion of the universe. So it makes sense that the radiation pressure from all that light, that escaping light, would have been building up there over 13.8 billion years and is giving rise to this accelerating expansion of the universe, and that is dark energy. We can also imagine that a cosmological constant may be given rise to by these electrons, since they absorb and emit photons all the time. These electrons will be emitting photons out into empty space as well. So you get things like the Casimir effect as a result of that, and various other things. Just this spontaneous emission of photons into space, and this cosmological constant, right? So, yeah, we get that also. And there's one thing else as well. If I've got time, so I've got 2 minutes left to do this for TikTok. So we can think of like two little hydrogen atoms in a box, and we can calculate the force of attraction between those in a sort of idealized box where there's no external gravity, right? There's no external gravitational forces in this imaginary box, just the forces generated by the two hydrogen atoms. So we can think about the two as creating a force of gravity via Newton's law. So that's G m1 multiplied by m2 over r squared equals F. But then also we have Coulomb's law. That's the electromagnetic constant, or the electrical constant there, or Coulomb's law constant rather. And we can start thinking about these both in terms of Newton's law and Coulomb's law, and we can get the same, almost the same result from Newton's law as we can with Coulomb's law, so long as we use this equation that I developed to assess what the extraneous electrostatic force of those two atoms is, and then put it into Coulomb's law, and we get almost the same number in terms of a force there. So we can say that F grav equals F elec, the electrical force, less radiation pressure, which was a touch I quite liked. So thank you very much for watching. It's been my rundown of quantum gravity. Love you lots. Bye.